Welcome to the start of our deep dive into ISO 21448, the international standard for the safety of the intended functionality, or SOTIF. As we begin, keep in mind that our primary objective is to master a framework that ensures the absence of unreasonable risk in automated systems. This roadmap is specifically crafted for systems engineers and safety managers who are responsible for bridging the gap between basic reliability and real-world situational awareness. In the world of modern vehicles, safety is no longer just about preventing a mechanical failure. It is about ensuring that a car's understanding of its environment, derived from a complex web of sensors and algorithms, is robust enough to handle the infinite variability of the road. Today we will explore how to build a safety case that can be trusted by regulators and drivers alike. To understand SOTIF, we must first embrace a major shift in engineering mindset, moving from the closed world of internal components to the open world of driving variability. Traditional functional safety, governed by ISO 26262, focuses on internal failures like software bugs or hardware short circuits. SOTIF, however, addresses hazardous behaviors that can occur without a system failure. Imagine a camera that works perfectly, but is temporarily blinded by the direct glare of a sunset. Nothing is broken, yet the system's performance is insufficient for that moment. We call these functional insufficiencies. Our mission here is to identify the real-world triggering conditions that activate these hidden weaknesses and ensure our system design can survive the messiness of the real world. One of the most frequent questions is whether SOTIF replaces traditional functional safety. The answer is no. They are complementary pillars of a holistic safety argument. Think of ISO 26262 as your guard against breakage. It uses ASIL integrity levels and redundancy to make sure the system stays reliable. SOTIF, meanwhile, focuses on limitations, asking if the intended design is sufficient for the target environment. While FUSA handles internal malfunctions, SOTIF handles external impacts like heavy rain, fog, or electromagnetic interference. By running these processes in parallel, we ensure the vehicle is both built correctly and designed for the right world, moving beyond the billion-mile testing problem through structured analysis and mitigation. The heart of SOTIF is this four-quadrant model, sorting scenarios by knowledge and safety. Area 1 is the known safe zone for normal operation. Area 2 contains known unsafe risks requiring mitigation or ODD restrictions. Area 3 is the critical, unknown unsafe zone of undiscovered black swans. Area 4 covers safe but unknown scenarios. Our mission is a continuous cycle. Discover hazards in Area 3, move them to Area 2 for fixing, and expand Area 1. We reach SOTIF release only when these hazardous areas are minimized to meet our safety acceptance criteria. This mission map outlines the iterative journey of SOTIF, moving through clauses 5 to 13 of the standard. We begin with specification and design at clause 5, but notice how the process loops. We identify hazards in clause 6, hunt for insufficiencies in clause 7, and apply functional modifications in clause 8 to close those safety gaps. Only after these design iterations do we define our verification and validation strategy in clause 9. Crucially, SOTIF doesn't end when the car is sold. Clause 13 mandates continuous field monitoring to catch unknown hazards we might have missed in development. This feedback loop allows for over-the-air updates, ensuring our vehicles grow safer with every mile they drive in the field. Everything starts with the operational design domain, or ODD. You cannot prove a system is safe if you haven't defined exactly where it is supposed to work. We draw clear boundaries around road geometry, weather conditions, lighting, and speed limits. In the SOTIF framework, the rule is absolute. If a car crashes outside the ODD, it's often a misuse case. If it crashes inside the ODD without a component failure, it is a SOTIF design insufficiency that we are responsible for fixing. This stage is iterative. As we discover new hazards during testing, we refine the system's dependencies and performance targets to ensure it stays within its safe operating envelope. In clause 6, we search for hazardous behaviors that emerge even when the system performs exactly as it was programmed. Think of phantom braking, caused by an optical illusion or lane drift due to faded markings. We evaluate these behaviors using a standardized risk metric: severity multiplied by exposure and controllability. We ask, how bad is the potential harm? How often will the car be in this scenario? And can a human driver or a fallback system intervene in time to prevent an accident? This step helps us draw a line in the sand for how safe is safe enough, identifying which risks are tolerable and which require immediate design modifications. Let's look under the hood at the causal chain of a hazard. A functional insufficiency, FI, is a hidden weakness in your design, like a LiDAR sensor unable to detect dark objects beyond 50 meters. That weakness stays latent until it is activated by a specific real-world triggering condition, TC. For example, a black car stopped on an unlit road at night. When that TC hits your FI, you get hazardous behavior. Our job in Clause 7 is to use methods like STPA, System Theoretic Process Analysis, to look for these causal factors before they lead to losses. By hunting for these black swan events systematically, we move scenarios from the dangerous unknown into the manageable known. When our risk evaluation shows that a scenario is unsafe, we have 4 primary strategies to fix it. First, system improvement. Can we upgrade the sensors or improve the algorithms to overcome the limitation? Second, ODD restriction. We can simply restrict the car from operating in heavy rain if we can't guarantee safety there. Third, HMI and misuse mitigation. We use driver monitoring systems and clear alerts to prevent inattention or misunderstanding. Finally, we have the degradation strategy. If the system hits its performance limits, it must transition the vehicle to a minimal risk condition, such as a safe stop on the shoulder. Verification and validation are the heart of the SOTIF proof. Verification asks, did we build the system right, by testing against our specifications? Validation asks, did we build the right system, by testing it against reality? We use a testing pyramid strategy. We start at the base with millions of repeatable simulation miles to find edge cases and, quote, corner cases. Then, we move to physical testing on closed courses for dangerous maneuvers. Finally, we perform real-world discovery on public roads to uncover the remaining, quote, area 3 feet unknown hazards. This layered approach ensures that by the time we release the vehicle, we have sufficient statistical evidence that the residual risk is at an acceptable level. Let's examine the fork in our safety strategy, verifying the known versus discovering the unknown. Clause 10 focuses on Area 2, known scenarios. Here, we use regression testing to provide documented proof that the functional modifications we implemented actually work as specified without introducing new risks. We are essentially double-checking our homework to ensure the known gaps are closed. Clause 11 transitions us into Area 3, unknown scenarios. This is the discovery phase, where we hunt for black swans, using exploratory methods like randomized fuzzing, fleet tests, and long-mileage endurance runs. Every time a new hazardous behavior is found, it moves from unknown to known, feeding back into our design cycle for refinement. The ultimate goal is to prove that the residual risk from both areas has been minimized to a level acceptable to society and regulators. Before we can release a vehicle to the public, we must answer, how safe is safe enough? We don't just guess. We use formal frameworks like GAMAB, globally at least as good as a human driver, or ALARP, reducing risk until the cost is grossly disproportionate to the benefit. The SOTIF release is a formal safety case argument. We are presenting documented evidence that all hazards, insufficiencies, and triggers have been analyzed, and that the design modifications we've implemented have reduced the overall residual risk to a level that society and regulators find acceptable. This is the final gate where we confirm that no known scenario poses an unreasonable risk. The launch of a vehicle is not the finish line. In SOTIF, the loop stays open. Clause 13 mandates continuous field monitoring after release. We track data on disengagements, near misses, and accidents to see if our original risk estimations were correct. If we discover a new unknown hazard or a context evolution, like new types of road signs or infrastructure changes, we analyze the root cause. If it's a SOTIF issue, we feed that knowledge back into the design phase, Clause 5, to trigger an over-the-air update. This ongoing feedback loop ensures that the vehicle stays safe throughout its entire operational life, adapting to the world as it changes. AI and machine learning introduce black box insufficiencies that traditional code doesn't have. Challenges like data bias, overfitting, and probabilistic uncertainty. To solve this, SOTIF integrates with ISO PAS 8800, which provides a specialized assurance framework for AI components. This involves a dedicated dataset lifecycle, the dataset V model, ensuring that our training and validation data are representative, complete, and free from bias. We decompose our vehicle-level SOTIF goals into specific AI metrics, like maximum allowed classification errors or, quote, ghost detections. By bridging these two standards, we can build a robust argument that our AI models are safe, robust, and reliable in the field. As we conclude, remember our mission: reduce the unknown unsafe. SOTIF ensures safety even without system faults. The ODD defines operating limits, and triggering conditions reveal hidden risks. The 5-step cycle: define, identify, mitigate, verify, and validate must run continuously. Keep improving until more scenarios move into the known safe category, and we build real trust in safer mobility. Thank you for your dedication to mastering this critical standard.